We look at the audible range of sounds for the human being, from something so quiet we can barely hear it all the way up to something that's so loud that it's painful for us to listen to. And we looked at those measurements in terms of pressure, the unit of pressure that we'd measure with a microphone. We will see that something that's barely audible, again, we have this 0.000063 pascals. Someone whispering in your ear, very, very small pressure fluctuations. And then if we go up a unit of description, so from barely audible to something we'd call quiet, we see that it's 0.00063, so we've dropped a 0. Go up to something we'd say moderately noisy, 0.0063, drop another 0. Something we'd go from moderate to noisy, drop another 0, it's 0.063. Something very loud like a heavy truck is 63 hundredths of a pascal, or 6/10 of a pascal, okay? And then go all the way up to something that's painful like a jet taking off, and we'd measure that about 20 pascals. So if we look at this range, we see it's an incredibly big range, right? Not very often where you're making measurements that you're writing down numbers like 20 and writing down numbers like 0.000063 in the same measurement, okay? Dynamic range of human hearing is very, very large, and this aspect of our hearing makes Pascal, the unit of pressure, kind of inconvenient for us to use. These numbers are so different that it's just hard for us, it's sort of awkward for us to use these.
I used to work at a noise and vibration department, Scott. Didn't you guys say oh, that one's much quieter, it's 0.0045 pascals, and no, this one's 0.0037, and was there a lot of 0.00 discussions?
There was initially, but they found it was costing so much time for us to talk that way that they decided to switch to something more efficient. So while I was there, they switched over from talking in 0.0000s to using the decibel. It saved us a lot of time, put our company back into the black. It was great.
0.00s or point not?
We were 0.00s, but there every once in a while someone would come over from Europe and they'd be
a notter.
0.0, yeah.
Aught?
The aughts. Yeah,
okay.
Knots, aughts.
This scale looks a little more reasonable here with these
it sure
decibels.
does, and that's the whole point, right? And so we're using this thing called the decibel, and so even lay people are often aware of this unit of dB or decibels for sound pressure. We're going to explain how it works so that you have a better understanding. But you see what effectively the decibels do is it squashes this dynamic range, and it makes the very low end or very smallest number and the very highest number a lot closer together. 10 and 120, those are both whole numbers, integers, so we're already a lot closer together, so it makes it much more convenient. And you see, before we were just dropping off a 0, so there's this factor of 10 built in, this sort of logarithmic aspect to our hearing ability. Those equate to some very nice round numbers in decibels, and so the decibel is going to be very convenient for us to use for sound pressure levels for a human being. So how does this decibel work? How do we convert from pressure in pascals to decibels? We use this equation, and it's really just a logarithmic ratio of two numbers. That's all a decibel is, and it isn't specific to acoustics or sound pressure. You can take any numbers and theoretically convert it into decibels. It's really just a logarithmic ratio. We use it for pressure because of those aforementioned aspects of human hearing. Okay, so we take pressure from our measurement microphone, we divide that by what we call our reference pressure, and we all need to agree what this reference pressure is. And then we take that ratio, take the log of that, multiply by 20. That's your sound pressure level in decibels. Okay.
Are you moving your laser pointer?
No, I'm not. I was waving my hands. I was gesticulating, but you make a great point. I should be using my laser pointer, particularly for you who can't see me or my video feed here. But you're right. We're making a measured pressure up here. We divide that by a reference pressure, take the log of that ratio, multiply by 20, and that's our decibel. Now you notice in this equation, we're always talking about this pressure that we're measuring as an RMS quantity. So it's important to understand it's not a peak or a peak-to-peak value, it's an RMS. And the reference pressure we'll use in all of acoustics is 20 micropascals, or 20 times 10 to the negative 6 pascals. Okay, and we'll talk about where that reference pressure comes from, but this is how you convert pressure into decibels. Okay?
Looks pretty straightforward.
Yeah. So if we look at this conversion for decibels, we'll use decibels, and we call it sort of the original sound quality metric. Sound quality metrics are trying to make sound and the qualities of sound, like amplitude or frequency, more convenient for us to use for human beings. Decibel takes that awkward Pascal scale for human hearing and converts it to something much more convenient, and it sort of matches our perception. So that's why we use decibels. So if we look at this conversion and we take that reference pressure and we plug it into that equation, so now we're measuring 20 micropascals, we divided that by our reference, which happens to also be 20 micropascals. That ratio becomes 1. And Pete, do you remember the logarithm of 1? What is
that's
that?
A big naught. 0.
That's right, it's always 0. So when you register 0 dB on your sound pressure level meter, that means you are measuring your reference. Okay. Now if we jump up to much bigger number, 1 Pascal, nice easy round number, convert 1 Pascal into decibels using that same formula, we'll calculate 94 dB. Okay, this is often used for microphone calibration. It's a nice round number. 94 dB equals 1 Pascal, and so it's just a nice convenient unit. Now, something interesting is I'm going to show you here where I take 1 Pascal and I double that, and I go from 1 Pascal to 2 Pascals. I've doubled the pressure. What happens to my decibel value, Pete?
Yeah, 94 to
Yes.
100 is a 6 dB
6
increase.
dB. Yep, so we went from 1 to 2, so an increase of 1 Pascal is 6 dB. But now what? Let me show you something weird. I'm going to double it again. I'm going to go from 2 all the way up to 4. So now my increase is twice as much as it was last time. Now how much does it go up?
100 to 106, 6 dB. So
6 dB.
Again, 6 dB.
Yes, so this is the price we have to pay for the nice convenient aspects of using decibels for human hearing. We have this awkwardness where you have to sort of take the good, take the bad, you take them both, and there you have the facts of the decibel. Where 6 dB is always a doubling in your root measurement. So no matter what, if I'm going from 2 Pascals to 4 Pascals or 100 Pascals to 200 Pascals, that increase will always just be 6 dB. Okay.
That's
so
crazy.
It's a little bit awkward. Yes,
It's
it's
like,
very
boss,
awkward. But
I've reduced the sound of the product by 50%. The sound pressure's gone down, and it's went from 66 dB to 60.
yes, and if he doesn't understand this aspect of decibels, you might be in some big trouble.
Yeah.
You'll find yourself talking in OOOs and nots.
Yeah.
Pretty
or
soon.
put on a special list and can end up working for Siemens or something.
We all end up here sometime, don't we?